Recording in progress.
Okay, so maybe we should start
Yes.
saying a few words first. Olga, you want to say something?
No, I think we don't have time because you see.
Yeah.
We
Well,
have
but
45
anyway,
minutes
I would
for
like
talk.
to. Yeah, I would like to say as the editor of the laser physics two journals, the laser physics journal and the laser physics letters. We are very happy that we are carrying on this workshop, and which somehow keep alive all our efforts towards this field. We all know that some topics that have regular meetings, sometimes they get out of interest and then they die out. But this is certainly not the case of laser physics. We are clear living a moment where lasers and laser physics is a fundamental thing for many things. And you see the applications in bio, the applications in communication, the applications in computer science, and a wonderful new field of things that laser is bringing to us. So for us, worth the effort to keep the workshop going. And hopefully next year we're gonna meet presentially. So after many years, we'll be able to get together, having those rooms filled with people. I remember one of the seminars with more than 100 people in 1980, just before the pandemic anyway. So it is very important for us to keep going, and I appreciate the positive response of all the community participating in this workshop. We're going to start in a special way. So we have with us Chris Monroe, or Christopher Monroe. Chris is an American physicist that started his career in Colorado, working with Carl Wyman, which is a guy that got Nobel Prize in cold atoms in Bose-Einstein condensation. And at that time, Chris was also very active in neutral atoms. But then Chris moved. He works with David Weiland. That's another Nobel Prize in physics, where he did many, many nice experiments with ions. And I think that turned on his desire for going on with this, even though in a way he did a lot of neutral atoms as well. I remember visiting him in many occasions. Well, then he was in Michigan, where he really did a nice work, start labs. But Chris is a kind of dynamical person. So he's always moving ideas, thinking out of the box, moving to new places for new challenges. And then he was in Maryland, together with the people in the NIST and University of Maryland joint project. And for many years, Chris was a seminal person there in these ion traps and progressing the ideas of computation using the ion array and everything. And then, of course, that was not enough. Along this way, he got many, many prizes. I'm not going to list Chris because it's a long way, but I remember when he was inaugurating the National Academy of Science, and was a pleasure for everybody there and for all the community that Chris became a member, and a very active member since his beginning. And then he moved to North Carolina, and he started a new, different challenge now he's facing, which is the establishment of a quantum center in Duke University. And of course, Chris is one of the main person in this quantum computation business. He's pushing not only the understanding and the science, but also the technology. So he's enthusiastic of starting those companies that eventually will take over the technology and make sure that this will be available to everybody. So Chris, we very much appreciate your time. I know it's very busy with so many things, and I appreciate you come and giving the opening plenary talk for us in the laser physics workshop, and speaking about a topic that's everybody hear all the time, and we want to know exactly how is that evolving and what are the perspectives. So thank you very much. I will give you a warning. The plenary is about 40 minutes, right, Olga? Open the microphone.
Yeah, I
the
think
microphone.
she said 40 minutes. Good.
Yeah, but I will give you a warning 5 minutes before, okay?
Sounds good.
Olga, if you open the microphone.
Yes, we have 40 minutes left for this talk, and it includes maybe about 5-10 minutes for discussion and maybe.
Yeah. Anyway, Chris, it's up to you. I know you have so many things to tell, but I give a warning 5 minutes before the end.
Okay,
yes.
sounds
Go
good.
ahead and thank you very much.
I'll make the time work. Thank you, very, very kind and gracious introduction, Vanderlei. Thank you, Olga, for having me here. Indeed, I will talk about how lasers are used in trapped atomic ions systems to build quantum computers. But I can't help in the introduction that Vanderlei crossed my career in two major ways throughout the years. I'll start with the second one. This is a paper we wrote, which you might say was maybe not so well motivated, but we were working with cadmium ions. And one feature of cadmium is that the vapor pressure of cadmium metal at room temperature is about 10 to the minus 12 torr, which means you'll always have a vapor, a very low level vapor. So it makes it very easy. The atoms are always there. So you can build a cell-based magneto-optic trap out of cadmium. The problem is it's really deep UV, 229 nanometers, really bad. And even more, when you do the laser cooling on the strong transition at 229, that's more than enough energy to photoionize from the excited state. So you're not going to get many atoms. You're going to make ions. In fact, that was the goal here, was to make ions from the MOT and load them in an ion trap. And so Vanderlei visited me in Michigan for almost a year, in and out with one of my students, Kathy Ann Brickman. And we did this, but this follows up work we did in 1992 at NIST in Boulder, where we actually made the first cold atom and trapped ion integrated in one chamber. We didn't write anything about it. This is 1992. And it became a little bit of a cottage industry about 10 years later. We really should have written something, but we had a lot of fun in Boulder in 1992. I just remember, anyway. So Vanderlei and I go way back, and I look forward to Vanderlei, you coming to Duke once again for an extended visit, and we can have fun once again. Okay, so let me get back to my slides then. So this will be a talk about quantum information, qubits, and controlling qubits to build quantum computers. It's an experimental talk, and I often show this slide, which is sort of a selection of the technologies out there that look interesting to build large-scale quantum coherence, qubit by qubit, single atom by single atom. And this is adapted from an article a long time ago in Science that the editors wrote. And of all these technologies, I've updated some of the parameters here. You don't have to just look at the nice, pretty pictures. On the right-hand side, we have what I call synthetic qubits.
We do not see your screen.
We cannot see your slide, Chris. You have to upload again.
Somehow it stopped sharing screens for me. Thank you.
Click on the screen and put in the presentation mode, and you'll be able to.
Do you see it now?
Yeah, we see.
Okay, very good. Sorry about that. Okay, so this is the slide I kind of stole from Science magazine. It shows the different technologies that are interesting with respect to qubits and making quantum computers, quantum communication networks, things like that. On the right-hand side, we have these synthetic qubits, I call them, and these are basically solid-state systems that they're generally cooled to nearly 0 Kelvin, almost to absolute zero, so that you can distill some quantum degree of freedom that can be controlled. Probably the most popular are superconducting circuits. These are big devices, of course, but when you cool them, you get an emergent degree of freedom based on the superconducting loop and a Josephson junction. You can store a 2-level system in the currents there. There are other technologies that are really, they haven't been built into systems yet, but they're very interesting physical systems that allow you to control quantum coherence. Some of them optically, like these color senders, the nitrogen vacancy in diamond, and others. But the superconductors really stand alone in the sense that they've been able to build these into big systems and controlling them with circuits. On the left-hand side, which is going to be the subject of my talk, especially on the trapped ion side, of course, these are what you might call natural qubits. These are quantum systems that are already composite particles. And the huge advantage to natural qubits is that they're perfectly replicable, right? Every electron is the same. If you use electrons or photons, neutral atoms, every atom of 171 ytterbium plus is exactly the same. In fact, they're decent atomic clocks. And this gives you one of the key requirements for scaling. That is, there's no yield problem. The yield of making atoms can be nearly 100%, whereas in these solid state systems, yield is a big problem for scaling. So this is a little maybe not obvious to some people. You build computers out of solid state transistors and you can scale them using VLSI. But in quantum, I don't really see how solid state qubits can be scaled, period. That's a pretty strong statement because there's a lot of research out there looking for maybe new materials that might allow that scaling, and that we're all looking forward to that. But let me put it this way. It's very hard to make a business plan out of current solid state qubits. I'll leave it there. Okay, so I'm going to talk about ion traps, of course, individual atoms as qubits. And here is a picture of a trap that was made by Sandia National Laboratories. And in fact, I carry one of these traps with me all the time. This is not Sandia. This one's made by IonQ. I'll talk a little bit about that. Now, the chip itself, there's nothing quantum about it. It doesn't have to be cold. It basically hosts electrodes that allow us to suspend atoms above those electrodes. And so this picture here is of 80 ytterbium atoms, 80. So there's 80 atoms here, each of them fluorescing in the blue, and it occupies a pretty small space above this chip. I've expanded the picture so you can see them. The atoms are about 1/10 of a millimeter, 100 microns above the chip. They're separated by a few microns. You can clearly optically resolve them. These little dots are roughly the diffraction limit of our optics. The atoms are laser cooled, and they're much smaller than these dots, maybe 1,000 times smaller. They're laser cooled to a few nanometers of position uncertainty. And all of this is in a vacuum. This chip sits in a vacuum environment. This is an AMO experiment, after all. And so clearly we're going to be using lasers all the time to initialize, measure, and control these qubits. I want to talk a little bit about that. Oh, and by the way, we store our qubit in a pair of hyperfine levels separated by 12.6 gigahertz. This is the atomic clock. We know that frequency to a hertz or even better than that if we need to. But when we make another ytterbium atom, it's exactly the same frequency. There's no manufacturing of atoms. Okay, so I want to go through very, very simple description of how we can, in a sense, wire together atoms using laser beams. The idea is fairly simple, actually. It involves something called a dipole force. And this is very popular now in neutral atom systems. You've heard the term optical tweezers. Well, we use optical tweezers all the time with trapped ions, not to trap the ions, but to actually push them around and exploit their Coulomb interaction in order to do something interesting. So remember, each atom has a qubit inside of it, and we're going to apply optical tweezers that apply a force, and the direction of the force depends on the qubit state. So in this picture, it's easy to imagine spin up and spin down. That's our qubit, 0 or 1. If you're in the state spin up, then you can imagine the laser force pushes up, and spin down pushes down. And when you do that to just two ions in a chain, the Coulomb energy of those two ions gets modulated depending on the qubit state. So if they're both in up or they're both in down, they both move up or down together, and their Coulomb interaction is the same. But if they're in the odd parity state, up, down, or down, up, then they're a little further apart, because they're on this diagonal, like down up. You'd have a little bit of a diagonal, and the Coulomb energy is a little bit lower because of that distance. And so when you calculate the defect in the energy, you end up with actually what looks like a dipole energy defect. And that makes sense because we're taking these individual charged atoms and making a little dipole moment, if you want. And so a dipole-dipole interaction will go like 1/r cubed. These are really big dipole moments, and they're engineered by the laser beam. Now, this is a very simplified version of what's going on. I'll go into more details in a minute. But if you look at the 4 possibilities of those 2 qubits, as I said, only the odd parity states have an energy defect, so they pick up a phase factor, a relative phase factor. And this is really all you need to entangle multiple qubits. This operation is called a phase gate, and when that phase is equal to pi/2, that gives you full entanglement. Okay, to get a real entanglement, you have to accompany it by pi pulses and pi/2 pulses, individual qubit rotations. But those are fast and easy and very accurate in this system. So this is really the bottleneck, this 2-qubit gate. Now, a couple of things I've simplified here. Number one, the force I've described, in fact, it's actually in the x basis of the Bloch sphere. So it's not a Stark shift or anything like that. So the energy, it turns out this phase works, it's diagonal in the x basis of the Bloch sphere. So the actual evolution operation is in Ising Hamiltonian. So it's an XX, sometimes we call it that. But the other sleight of hand, the other thing I simplified is maybe obvious from this picture here. When you poke just 2 atoms, all of the atoms are going to know. They're all going to vibrate like masses on springs. And so you have to deal with all those modes of motion. Now, the good news is when you deal with all the modes of motion, you no longer have a 1/r cubed interaction. It's independent of distance. In other words, the interaction strength really doesn't matter because these normal modes are non-local, okay? The bad side is that you have to deal with all that motion. It gets entangled. And so what we do is laser pulse shaping. We don't just push these atoms we don't just push the atoms up and down. We actually apply a very complex laser pulse shape that makes sure, we have a lot of bookkeeping, it makes sure that all the motion ends up at the end of the operation back to where it started. And so there's classical complexity in this gate. But because it's classical, we're not afraid of it. This is more of an engineering thing. Doing laser pulse shaping, we need pretty fancy optics to do that. And so the gate times are much slower than the normal mode frequencies, which are typically megahertz. So the gates are many microseconds, tens or even hundreds of microseconds. So all the modes, you really need to think about normal modes of oscillation. And the fidelity of these operations is quite good. It's approaching 99.9% in some systems. And so here's a little animation of how you build a quantum computer out of the trapped ions. And I skipped the initialization and measurement step, but this is just optical pumping. The first step optically pumps each atom to the 0 state. And by the way, up here is a quantum circuit space-time diagram. We have 7 qubits vertically, and time goes from left to right. And these boxes in the middle are gates, and this is the program that we're running. And in the ion trap version, these gates are basically laser beams that are scanned to hit multiple ions. And you can see when we hit one ion, nothing, I mean, it just rotates that. But when we hit multiple ions, they fuzz out. There's a force on them. And so there's a lot of computer science I'm missing here because an algorithm is now distilled to a bunch of gates. And then at the end of the day, we do not optical pumping, but spin state sensitive fluorescence. And again, the selection rules of our atom allow that. When you're in a particular state, it fluoresces. When you're in the other qubit state, it's dark. And then you just read out which atoms are bright, which are dark, and there's your answer. Well, I keep calling this a quantum computer, but if you look in a laboratory that hosts such a system, it looks like this, which is a typical AMO experiment. It doesn't look like a computer. And I said the words business plan before. It doesn't look like a business plan either. it's very difficult to imagine scaling this. This experiment actually only has a couple of ions in the vacuum chamber right here, but the infrastructure of optics is really severe. And so you can see the role that lasers and optical systems play. And of course, this is an experiment. It's meant to be flexible. We're doing research on this. We want flexibility in all of the things I just talked about. But if you know what you want, you can really condense any optical system and add a healthy dose of engineering. You don't need every mirror to have 3 knobs, 3 adjustments on it, for instance. So over the last several years, we designed and built basically put everything you saw into a box and froze the design, and anything that we need to adjust, we put on electronic mounts that come outside that box. And this is really there's a lot of engineering here. And in fact, it strains the budget of what we can do at the university. So under the funding of IARPA and NSF in particular, the NSF STACK program and the IARPA MQCO and Logic programs, we were able to contract with Sandia for the chip traps, L3Harris for very fancy optical modulators, and other companies you might recognize to help us integrate and build very well-engineered optical solutions. And my colleague at Duke, Jung-Sang Kim, has worked very closely with Cold Quanta on actually making a vacuum chamber really small. And that vacuum chamber, it seals right on the chip here with the indium seal. And you can see the windows here. So even the vacuum, at room temperature, the vacuum is very small. Now there's an ion pump not shown, but it's very small. It comes off one of these edges. And so we worked closely with Dana Anderson and his colleagues at Cold Quanta, although Jung-Sang really, actually, he has all the IP on this stuff at Duke, and IonQ is licensed, it turns out. But it's been a nice collaboration with all these optics groups. Now, when we built this system, we noticed we weren't always doing atomic physics in a system like this. When things are aligned, we can run circuits and start to think about compiling them and run algorithms at a very high level. And this is what we might call the quantum stack, quantum computer stack. And here, my expertise is really down to the bottom here, how to make ion traps work. But I mentioned that pulse shaping is complicated, and you have to engineer laser pulse shapes with some devices like multi-channel acoustoptic modulators. And then the XX icing gates we have need to be transferred to controlled knot gates. These are sort of the textbook gates you see in quantum computing, C knots and Hadamards, but we don't have those in the lab. So there's a nice opportunity to compress and compile gate-based circuits and then realize high-level algorithms and applications. So that was very eye-opening for me because the field had moved away from physics, from atomic physics and even physics, and into engineering, electrical engineering, computer architecture, computer science, mathematics, algorithms, information theory. So it's a very exciting time. And in the system we built, we started getting lots of inbounds, lots of interest on running applications and different research directions. I should update some of these references, but you'll note that these collaborators come from all over the place, all over the world, industry in some cases, government labs and universities. And I should acknowledge my 3 colleagues who are now at Duke, Norbert Linke, Marcos Cetina, and Crystal Knoll, all junior faculty in physics and ECE here at Duke. They were really important in connecting us with many of our colleagues on running these circuits for scientific applications. And I want to give a few examples. I'll probably have to go quickly through this, but here, this is one. You might is it down here? Yeah, I don't see it. Quantum scrambling and black holes. This is with Norm Yao and Benny Yoshida, and also Lenny Susskind advised us a little bit in the early stages on this. So this is a quantum circuit. And what does this quantum circuit do? Well, it turns out if you initialize one of the qubits in some arbitrary state and you set the others in a standard state, 0, these EPR blocks are just quantum gates that entangle. They make EPR pairs between the 2 rails. So this is a two qubit gate here and here and here. Well, here we have a unitary, and here we have its inverse, its Hermitian adjoint. I'll talk about these Bell measurements in a minute. Now, it turns out there's a property of unitary operators in quantum mechanics called scrambling. Now, a unitary scrambles if it produces entanglement at all depths, at all levels. And so it's not just entanglement, but it's higher level entanglement. And again, entanglement's a pretty complicated concept anyway. And scrambling has become very interesting, actually, in the context of black holes and quantum gravity, believe it or not. And I will test the limit of my understanding by trying to explain it to you. But when you put a qubit into a black hole, it is thought to quickly scramble with all the degrees of freedom of the black hole. And there's some theories on the entanglement entropy of the black hole and how it follows an area law instead of a volume law. Lots of interesting things. But scrambling is something that's really hard to measure in the laboratory. And this circuit actually does that. And the way this works, again, Norm and Benny kind of showed this to me many years ago. If we apply some unitary and its Hermitian adjoint, and we measure a Bell pair on any one of these three pairs, it doesn't matter which one. If we get a successful Bell measurement and U is scrambling, then this input qubit will be teleported. It will find itself on the last rail in this circuit. So that teleportation happens if and only if U is a scrambling unitary. And you need at least 3 qubits for scrambling. With 2 qubits, there's just entanglement. You can only have one depth of entanglement. So there's no concept of scrambling. So this is the minimal version of it. And if you want, you can say this is sort of like 2 black holes, one running backwards. Okay, so it's not really a black hole. It's an analog to a tiny black hole, I guess. And this is data here where, what did we use for U? It's actually a circuit. We broke it up into these x-axes and rotations. And you don't have to look too carefully here, except there's a parameter theta in these rotations. And as we vary theta, we expect we can change whether U scrambles or not. When theta is 0, there's no scrambling. It's just near shallow depth entanglement. But when theta is pi over 2, we expect this to fully scramble. And we indeed see the teleportation fidelity goes up from the classical value of 0.5 up to 0.75. It should have gone all the way up to 1. But this is actually for 2017. This is a pretty deep circuit, and we had decoherence. But because it's above 0.5, we can say conclusively that there's scrambling. And this is separate than if U and U dagger aren't exactly opposites, or if there's decoherence. That doesn't cloud this observation. So it's, if you've ever heard of I forget the acronym for when you evolve a quantum system forward and backwards in time, out of time order correlator. When you measure those are sensitive to decoherence and not reversing things perfectly. This circuit's not, so in a sense it's more powerful. Now we've been recently working on inputting a thermal field double state into this circuit, which has other analogs to black holes I won't get into, but it's a very exciting field right now. Sorry, I didn't mean to take too much time on that. In fact, how are we doing on time? Yeah, we're okay. This experiment also...
You still have more than 10 minutes, Chris.
Yeah, we're good. So Norm Yao and Umesh Vazirani, also Thomas Vidic at Caltech. Norm used to be at Berkeley. He's at Harvard now. Umesh still at Berkeley. These were 2 circuits that they're sort of like Shor's algorithm. Now, and this is the topic of verifying that you have a quantum computer. And you may know that if you have a generic quantum computation, it does something really hard that you can't do with a classical computer. So how do you prove that you have a quantum computer if you can't tell classically? Well, one way is to calculate one-way functions, like Shor's algorithm factors big numbers. And we know that a good challenge to somebody with a quantum computer is to give them big numbers. And if they keep factoring big numbers, you must conclude they have a quantum computer. But you don't need a quantum computer to tell that. All you have to do is keep secret the factors of a big number and do it that verification like that. Well, these are 2 examples, some similar to that, but they're easier than Shor's algorithm. This bottom one in particular looks a lot like Shor's algorithm. It's not x to the a mod n, it's just x squared mod n. And this is a 2-to-1 function. It's called a Rabin cryptographic system. And it's irreversible function, and we can use it to show for realistic quantum computing systems that you can certify that you have one. And it relies on the inability to factor the number n, like Shor's algorithm, but the circuits are easier. In fact, I'm gonna go real fast through this. This was not a quantum supremacy experiment yet, because our computers are still too small to be able to we can model what goes on classically. But unlike Shor's algorithm, we think that we can use one or both of these applications to prove a quantum computer with maybe 1,000 qubits and maybe 10,000 gates. And this is something that's going to happen soon. It doesn't require millions of qubits and billions of gates like Shor's algorithm. So, okay. So one technical advance that we used in that experiment was the idea of partial measurement, measuring some of the qubits, a subset of the qubits, while not affecting the others. And this was afforded by the architecture of ions. We can actually move them around in space and detect some of them without the scattered light destroying the others. And so we implemented that in our system at Duke. One last example, this is more of a quantum simulation of a condensed matter model. So I mentioned the icing interaction we have. Well, if we shine all the beams on all the atoms, then we have an all-to-all icing interaction. In fact, it's not short range, it's not just nearest neighbor. So that's a pretty interesting Hamiltonian. And when we put a transverse effective field, these are just Stark shifts that shift each qubit individually. In fact, this is a global Stark shift on all the spins. So this is a transverse field icing model. We've done a lot of work there. But with Diego Porras in Madrid, we've implemented the SSH, the Schrieffer-Heeger model, which we do this by adding a harmonic transverse magnetic field. So this oscillating field is just a sigma z field, but it works with pairs of spins. It pictures a lot better than words here. So we're basically oscillating the transverse magnetic field here, transverse to the icing interaction, but we're doing it with a phase shift on every other ion, if you see what I mean. So these blue bars denote the field, the effective field we're applying. And when you do this, and you might know that when you have a harmonic Hamiltonian, you can always make an effective Hamiltonian based on that harmonic Hamiltonian. And when you do this, the effective Hamiltonian is just a so-called XY model, a flip-flop model, where spins can hop from one site to another, but the strength of the interaction varies. It's strong, weak, strong, weak, strong, weak. And that comes from this funny pattern of the oscillating field. So this is the SSH model. When delta, in this case, when delta is less than 0, we have it in this phase, but we can also do this phase, where we start off with two edge qubits that are sort of alone. This is the interesting one on the right here. And so we end up with a weak, strong, weak, strong, weak, strong. The edge ions have only a weak interaction. And the reason I'm giving you all this background is that this model, the SSH model, admits an edge state, sort of a long-lived topological edge state. And so it's a way to simulate some of the topological magnetic models that we see in condensed matter physics. And that's really it. And so in this experiment, what we did is we did something very simple. We prepared that Hamiltonian, and let's pay attention to the right two graphs here. We excited a single spin in the bulk, in the middle of the chain. This is a chain of 22 ions, by the way. Sorry, let me go through the animation here. Where is it? There, okay. So we have 22 spins, and there are a couple on the edge that we didn't use. There are 27 qubits total, and we ignored the first two and the last three. Okay, so there's 22 spins, and so the bulk means, anything but 1 or 22. So we make an excitation here in the middle, and it sort of dies fast over time. Whereas if we excite on the edge, either on the left edge or the right edge, it lasts longer. This is all preliminary data right now. We haven't written this up, but there's a clear difference. The edge excitation is much longer lived, and it's due to the stability of these edge states in this SSH Hamiltonian. So it's just an example of using a quantum computer in simulation mode to study things that are very interesting. And in some cases, 22 is not a lot, but if you have several hundred qubits, these are things that you can't easily calculate. And for instance, one thing we're going to be interested in is how does the excitation vary with distance from the edge? These are long-range interactions. We expect to see some type of a range there. Okay, so I'm going to close in the next few minutes talking about the engineering aspects of this. We have a machine. It's capable, certainly, of science, but is this really a device? Is this a computer that a third party can use, sort of like your iPhone, without caring what's inside? Well, this is the story of the company IonQ, which has done exactly that. And so Jungsang Kim and I, here you can see Jungsang in the middle here. That's me over here. Peter Chapman is our CEO right now. And IonQ became a public company a year and a half ago, partly by accident. A lot of it had to do with COVID. Because we were able to go public, it means we don't have to raise money from venture capital, and that's become very difficult. So we were sort of lucky to do that a few years ago. Now, being a public company also means you have to do certain things, like have quarterly earnings reports and so forth. But we're very well funded now with public investment, and we can now make many generations of quantum computers and try to work with customers to really scale our systems to be commercially valuable and useful. And this will make it very, very interesting for academics, because when there's a device out there and people are interested in it, it makes the research just go into high gear. And one thing I noticed, I've put some of these numbers together. The amount of money that the U.S. has invested in ion trap quantum computing is pretty phenomenal over the last decade. And a lot of this, it's dominated by the two companies, IonQ and Quantinuum, which spun out of Honeywell. But also there have been these programs I mentioned, the Pl.1, that has funded ions at a high level. So there's well over $1 billion that's been invested just in the last 10 years in trapped ion quantum computing. So that's a very good sign. It means we can start to do that engineering. One of our latest generation quantum computers is called Forte. And this is a picture of 35 ions in a chain. And we just used the central 31 ions. And with 31 ions, 31 qubits, there are 465 pairs. And we've demonstrated 2 qubit gates on all 465 pairs. And this is a histogram of the errors that we see. And the average error is at about 0.4%. But we also know that the fundamental error is about 0.01%, about 10 to the minus 4. And this has to do with scattered light from our control beams, our optical tweezer beams. And so what that means is that these errors are largely control errors that we are putting on the system. And so that means there's lots of promise to get rid of them. Put it that way. It has to do with optics, and our optical systems are still big, and we're trying to shrink them down over time to get this even better. Maybe I'll skip over this. This is the latest measurement of something called algorithmic qubits. These are qubits that are also useful. It's sort of the minimum of the number of qubits you have and the square root of the number of gates that you have. Because if you have n qubits, you need roughly n squared gates to do stuff interesting. So when we get to AQ60, things are going to get very interesting because you can't simulate. And this is a picture of another picture of one of those vacuum chambers I showed you before. IonQ, of course, is working with companies along many different directions. Again, all of these applications are still small, and you can simulate what's going on in a classical computer. But as we scale up our system and we know how to scale them up, I want to talk for 1 minute on that. We expect some of these will actually create commercial value, from finance to machine learning, pattern recognition, and even molecular simulation. So how do we scale? I'm showing you pictures of just 20, 30 qubits. Well, one way is to shuttle. There was a hint of this in one of our experiments, the certification experiment. You can shuttle atoms between different clusters, different chains. And so at IonQ, we've been playing around with an architecture that has 4 separate crystals, 16 each. And this is real data on the top. Of course, this is all animation below. But we have 4 times 16, and we bring any adjacent pair of 16 into 32. And that allows us to do gates over 32. And then you can propagate the entanglement that way. All the time, we're sort of minimizing the number of ions that are in one chain. You can't have 10,000 ions in one chain. It's just too, it's too noisy. So that's one way to modularly scale. And I would say Honeywell, this last reference is to Quantinuum and Honeywell. They've really used this in their architecture and are getting some great results there. Now, the second way to modularly scale is to use optics, use single photons. And we know we have protocols how to move information from spin qubit to photon, and then have a classical optical switch that allows you to have a fully connected quantum computer over many modules. So it's almost like a data center now. Now, the price here, and it's a big price, is that this photonic interaction is very slow. When we started doing this, in fact, my lab at Maryland was the first to do this in 2007. The rate of entanglement was 10 minutes for a single entangling pair. Okay, so that's really slow. But this is getting a lot faster over the years. Right now, it's at about 1% of the gate speed within a chain. So things are starting to get interesting there. That was from the group at Oxford, Chris Balance and David Lucas and so forth. So this is a technology, I think no matter what qubit technology, eventually you're going to have to do this, exactly this. You're going to have to move to photons and send it through an optical switch. I think people are starting to recognize this in any platform. But the platform of ions is interesting because as we get more powerful and get more qubits, the system's getting smaller. That's really what you want. That's what Moore's law was about. And I don't see this type of evolution in any other technology out there right now. In superconductors, as you put more qubits, the refrigerator gets really big. The latest Google refrigerator is as big as a building, what they're designing. So there needs to be a lot of research and breakthroughs in just supporting the solid state system. Whereas because of optics and lasers, we can imagine blowing a lot of the stuff, a lot of the circuits, optical circuits, right on the chip itself. There's some great work at ETH Zurich and NIST and other places, Lincoln Labs, starting to integrate things on chip. And then finally, I'll just skip over this. I didn't want to talk about error correction because I don't think it's really needed, and it may never be needed in the way you think. But error mitigation allows you to take advantage of the structure of errors. And I'll skip over this. I wanted to make a comment. If the companies are going to make all these great things, where does that leave us at the universities? Well, I hinted at this earlier. If companies make great quantum computers, it's just going to multiply the possibilities for research. And at Duke, we formed the Duke Quantum Center that is sort of a user facility model. And with my colleagues in ECE and physics, mostly a little bit of math and chemistry, we build several quantum computer systems and use them. We use them for applications, but they're scientific applications, not commercial applications. And so we have 6 systems, and there's a 7th that we're designing right now. The so-called blue system is the one that we've leaned on as a lot. Gold is replacing that. Jungsang Kim and Ken Brown run red and purple. Norbert Linke runs silver. Ken Brown gets to have his own name on this one we call the Brown system. But these systems at Duke allow us to once again work with scientists in many different areas. And this idea of co-design, quantum co-design, learning about algorithm structures to help us build new systems, also allows the theorists to dive deep down and understand our icing model or the native connectivity or the native gates that we have. And that's sort of vertical. The vertical development of quantum computing is really important. And this Duke Quantum Center is really unique. It's the only one in the world that really has a vertical research approach in quantum computing. So this is a list of folks in my group, the ones in bold. People that have left my group over the last decade are listed here, and most of them are still in the field. So it's very exciting. It's a growing field. Obviously, a lot of company employees that left my group. But and I'd like to again acknowledge NSF and IARPA in particular, also the DOE QSA program for support of this work. So thanks very much.
Thank you, Chris. I did not stop because you were coming to the end, and we still have minutes for questions. So thank you for the nice talk and an overview of. Very nice to see that developing technology just push science, not suppress science. This is great. Okay, the talk is now open for question. I just ask you to be brief on the question, and Chris to be brief on the answer. So, first question. Vitaly, you want to ask your question? No.
I have a general question. Is it
okay? Go ahead.
Chris, is it possible with your system to calculate really a number p hat for classical computation quantity using your system as a quantum simulator, as for the some model, condensed matter model you discussed? The point is that your Hamiltonian is, of course, a percent or so different from that model.
So let me try to repeat your question. So the question is, can we do simulations? So when we implement a quantum simulator and we claim there's a certain Hamiltonian here, there are of course other terms, in the coupling that we neglect, or there are approximations. Is that your question? How faithfully can we implement a target Hamiltonian?
That model generates some quantity which is number p hat for computing. And your system, in principle, could be used to calculate this quantity. But because of difference with the, well, you said, of your Hamiltonian with the real, this kind of Hamiltonian, is it possible to do in principle? Because all number p hat quantities computations relies on the exponentially small oscillating terms, which should be exactly taken into account.
Right. So in this example, for instance, when we form the effective Hamiltonian, there are small terms in this Hamiltonian that I'm neglecting to write them down. And the question is, do they influence the observed, the measurements? In fact, yes, they do. And our theory, since these simulations are still small enough, our theory can fully take those things into account. And again, I'm not sure I'm getting at the answer to your question. These are simulators. They're idealizations in a way. We are neglecting small terms, but it is important to note that we can bound those terms. We know what those errors are. And we know the parameters that determine the strength of those errors. And by, one technique is by varying the size of the errors, we can back out, we can back out or cancel in some cases the influence from those errors. And that's what I would call generally error mitigation. Understanding what you're doing and that there's structure to the error that you have. It's not like you have a T2 decoherence, an unbiased noise on all the qubits. That you can do nothing about except fully blooded error correction with extra qubits. But here, the errors, we know they have a structure. They're Hamiltonian errors, largely. They're almost all Hamiltonian coherent errors. And there are ways that we can, even in the laboratory, get them to reverse out, like a spin echo in some cases. But it's a good question because every simulation has its own type of error that you have to really work on. I hope I answered.
From your answer, I understand that in principle it's just allowed to calculate rough quantities, not exactly number p hat quantities, like in real physical system, in a sense.
I didn't quite understand that term. You said I heard p half or something. What? Number
p hat for computing quantities like Heffnians or permanents cannot be calculated in this quantum simulator mode. You need to use your system as a universal quantum computer to do so.
I see. You can always, you can take any Hamiltonian and break it up into gates. And you do have to bound the errors on the gates. That's for sure. That's a very powerful way to go, but it's also painful in the sense that you're very sensitive to errors when you do that. But yeah, this system can do both simulators and gate model. It can do adiabatic manipulations, annealing, it can do measurement-based quantum computing. It's a very general approach.
Thank you.
Okay, Chris, thank you very much. Thank you, Vitaly, for the nice question. I think the second one to raise the hands is Ranjit. Question?
Yes, thank you for your talk. Do you measure the level of entanglement before running any algorithms?
Yes.
Whether state is maximally entangled or not, or whether.
Oh yes. In when we run any experiment, simulation or a gate-based model, there's a lot of calibration that goes beforehand, and we have. The architecture of this quantum computer has a bunch of beams basically that hit these atoms, and we have to calibrate every single beam. We measure their start shifts. We run every pair of gates, and measure the errors in those gates. And we do that by measuring in two bases. It's like there's an entanglement witness. We can measure for 2 qubits. It's very easy. It's kind of a standard thing. We measure how the parity of the states oscillates with twice the normal Rabi frequency. That's technical. But the laser beams drift, and we have to calibrate those all the time. We probably spend a quarter of our time calibrating. And so in the course of that calibrating, yes, we measure entanglement witnesses very directly. And then hopefully the system is not drifting, and then we can run the whole circuit and gather the data at the end of that.
Mm-hmm. Okay,
Okay.
thank you.
Thank you, Chris. Thank you. Alexei, you have a question?
Yeah, a quick one. In terms of scaling, designing a two-dimensional system, is that an option?
It is in principle. It turns out these ions are a few microns apart. And if you want to make a 2D grid of ions that are 2 microns apart, you need electrodes to have influence over 2 microns. And that means that the ions are going to be about 2 microns from the surface. As soon as you do that, you're very sensitive to noise on the surface. It's nice being really far away. There's something called a penning trap, where you get a disk of 2D ions and they spin. And John Bullinger and others at NIST really have a wonderful apparatus there. It's really one of the few in the world. But the quick answer is no. It's not a natural. It's not a natural geometry. That said, even though this looks like a 1D crystal of ions, the interaction is all to all. So in fact, 2D is probably the hardest thing we can do. We can do 36 dimensions. That's easy. I mean, here we have 80 dimensions, 80 ions to 80 dimensions, because everybody interacts with everybody else. It's all to all. But, it's a good point, because many materials, interesting materials, are 2D, and you really want to do 2D. We can, in principle, engineer 2D out of this 1D, but it's very unnatural. It requires a lot of headroom, a lot of gates to do that, But so it's sort of a yes, no. I want to stray toward the no answer. We want to avoid that if we can. But I think you bring up a good point. There's lots of interesting things we would love to do in 2D.
Thank
Okay,
you.
thank you, Alexei. Thank you, Chris. And now the last question by Olga.
Well, it's a similar question about scalability. So, in fact, you have 80 ions, but you are using only 20 or 30. What limits it? And if there are any other ways for scalability, you mentioned only one optical connection between different chips. Is there some other idea? Well, you discussed already 2D, but something else.
Yeah, it's a very good question. And I guess the answer, why don't we use more ions in a single crystal? It has to do with the fact I mentioned that we couple to all the normal modes. And when you get too many ions, there are very low frequency normal modes that are very noisy. And the bigger the ion string, the more those tend to affect things. In fact, it's the axial slow motion that's a problem. The ions just get fuzzy. And if you're focusing a laser beam, like we obviously are doing here, if the ions are fuzzing out axially, that's a problem. So I think the number is between 30 and 100 that we will have in a single chain. Now, the long term, the out game for scaling is optics, but in between we can move ions around between chains. I showed a slide on that where you might have 32 chains, each with 32 ions. So that's 1,000 qubits, and you get to move those crystals together. And when they're together, you can do the entanglement and then separate them. And the act of moving atoms around doesn't affect the qubit, because the qubit is the hyperfine levels. If you've ever seen a cesium clock, the cesium beam clock, they send atoms in a superposition several meters, and it remains a superposition. So it's no problem. There is a relativistic shift, a second order Doppler shift, but that's really small. But the qubit can remain very coherent, even though you're moving it between. And that's not slow. That can be microsecond type timescales. So that's sort of the intermediate way to scale, is to move ions around. But you're right. I think the ion technology, the big indictment is that, well, you can't scale. Well, what does that mean? if you want 1,000 qubits, you better be able to do 1 million coherent operations. So that means you need part per million errors. Nobody has that. So when you say you can scale solid state by printing 1 million qubits, who cares? Because they can only do a few operations. If you can only do 10 operations, why do you have 1 million qubits? It's a good question for some big companies.
Thank you.
Hey, Chris, thank you very much. Thank you, Olga. Was a really nice talk and very clear and put us in a route of these new technologies of quantum. So thank you very much. I think we all appreciate. And now we're gonna have to move to the second plenary talk. And thank you very much, Chris. It was a pleasure to see you again. Thank you.
Thank you all. Look forward to Peter's talk.
Yeah. Okay, so now we're gonna Olga, I'm the one that has to introduce Peter, right?
Yes.
Okay, you gave up everything, right?
Oh, well,
but it's a pleasure to.
I'm chilling tomorrow. It's your duty today.
Oh, tomorrow is okay, fine. So it's a pleasure for us to have Peter Homenhoff from Germany to come and give a plenary talk for us. Peter has a very nice story. I remember him, he works with Teddy Hash in the very beginning of things, and he passed to Stanford, and he had a big movement around with many possibilities and start a very interesting group. Peter has many interests, and I cannot really point what is your most important interest, because you work with short pulses in a so large variety of things that we cannot really point, and all very interesting topics, from ships to electron emission to really accelerating charges and producing accelerators with short pulses, and so many things that we are so excited about. So it's a pleasure for us to have you here, Peter. You got many prizes. I'm not going to list them, as I did not list it for Chris, but you are one of these prominent scientists that is giving us a lot of hope for the use of short pulses in many aspects. So it's a pleasure to have you here as a plenary for the laser physics, and I thank you in advance for you accepting. And your talk is about 40 minutes, and I will give a warning when it's missing 5 minutes if necessary, okay? So please, if you could upload your transparency and we can start.
Thank you so much, Vandali. Can you see my slides?
Yeah, we can see.
Perfect. Thank you. Thank you very much for the wonderful introduction. Thank you very much for inviting me here, giving a plenary lecture. It's always a pleasure to be at the Laser Physics Workshop. And of course, it's a very special pleasure, and I really feel privileged to speak after Chris. I've met Chris many years ago when I was in Cold Adams, where I, of course, know your name very well, Vandali, 20 years ago with Ted Hensch. It was fantastic times, and ever since that, of course, I've followed the field. So fantastic to see. And what's great, we can be part of IonQ now just by buying stocks. Of course, I'm a proud owner of IonQ stocks, that's clear. Excellent. So let me take you to another field and really switch gears. Let's look into what you can do when you have really short pulses, phase-controlled laser pulses. And I want to give you 2 examples around strong field physics at the surface of solids, so at the surface of a needle tip, like shown here, and inside of graphene, like shown here. And this all relates, of course, to, whoops, hold on. Here we go. This is as you see, strong field and attosecond physics, a session chaired by these 2 gentlemen. I, of course, thank them and Olga very much for inviting me here. Of course, it would be an even greater pleasure to see you all in presence, but it is what it is. So what is this about? What's strong field and attosecond physics about? I think I don't have to introduce the topic, but just to get everybody somehow come from cold ions and the fantastic quantum computing stuff we just heard over to ultra-fast physics. It's about this line versus this line, right? You all know this famous discovery paper here, where some heroes in the field realized that when you look at harmonic orders, that they don't drop like you would expect with this blue line here, so that even the 7th, 11th, or 13th order would be entirely invisible. No, they discovered this plateau here where the relative intensity of these higher harmonics almost stays constant. This, of course, really then opened the field of strong field and attosecond physics. Ever since 1987, there's a lot of work going on in molecules and atoms. And what is this about? You've seen all this, you've probably all seen this famous picture. What it's basically answering the question, what happens if you put an atom, molecule, or also a solid tip, like I will show you, into a strong laser field? And there's just one cycle of laser field shown here. And this is the dynamics that you can somehow think of when you think of an electron as a point particle, which, of course, on these length and time scales, that's certainly not such a good approximation. But the main part of the physics is captured this way. So when the electron is ionized by the strong field, it rolls down this potential hill. When the laser field flips sign, the electron is accelerated back to its mother ion, only to either kick out another electron or to recombine and send out a high harmonic photon. And it's this very principle that governs strong field and attosecond physics. And on top comes, of course, that the electron is a matter wave that you can coherently control. And you see all kinds of beautiful matter wave physics, which I also like to show you in the first part of this talk. These are three heroes of our field that you all know. I just want to show them here because they received the 2022 Wolf Prize in Physics, which I think it's also a fantastic accolade for our field that has always been present in the laser physics workshops already for many decades. So what I'm talking about today is, can we measure really what exactly happens at the surface of such a needle tip when we shoot, say, 2-cycle laser fields at this metal? It's nothing special. It's just an edge tip. We can make it very clean. So here you see a field ion microscope image of the tip. You see the threefold symmetry here. You see individual crystallographic planes. You see 3 atoms sitting here. So we know it's clean. It can be very clean. But other than that, it's just a regular metal. And we were wondering, can you also observe similar physics? Can we see multi-photon physics? Can we see the strong field physics of electrons emitted from the needle tip here? And for example, you can ask the question, can we see the transition from multi-photon emission, where the multi-photon emission rate, as you all know, of course, follows the envelope of a laser pulse, right? So we don't actually see the carrier field in the rate which follows the intensity of the laser to the nth power, where n is the number of photons you need to get an electron above the barrier. And what happens if we crank up the laser field, meaning what happens when we make the famous Keltish gamma parameter, which I'll detail about in a minute, smaller than 1. So when we go into this optical tunneling regime, where now the laser field is so strong that it modulates the barrier up and down, so that electrons can tunnel every time the barrier is bent down. So here now the optical field is slow compared to the electron dynamics. And that's why it's kind of natural that now the electron tunneling rate really follows the field. So every time the field is large and negative, the potential is bent down and electrons are basically sucked out of the surface. And this is what Misha Ivanov and others have predicted for this tunneling rate is then clearly field resolved, also in the case of a metal. And can we measure this? Let me just show you some very old data that was very encouraging for us. We saw when we shoot these laser fields at our tip that electrons are emitted, and we show here spectra, and you see these bumps here, see these maxima. These are photon orders. You see right away, these bumps are spaced by 1.5 eV. So what we see is clearly above threshold photo emission. We see the leading order, and then we see higher orders, and we see these clear bumps, which means that the laser really couples coherently to the surface of the metal. So the electrons are really emitted in a coherent fashion, forming these multi-photon emission orders. Then what happens if we shoot stronger fields? Then, of course, you know that the carrier envelope phase can get important. The carrier envelope phase is the maximum of the difference between the maximum of the envelope and the maximum of the carrier field. So here we just scan this carrier envelope phase. If you see carrier envelope phase effects, you can right away infer that, okay, now the field of the optical pulse gets important. And this is what we saw. So here we just look at these spectra. and see that when we vary the carrier envelope phase, we just see photon orders appearing, disappearing, very different spectra for different carrier envelope phases. We can also model this. I don't want to go into detail. The nice thing is here, you can think about it differently. Here, it's now the effect of a very short laser pulse that emits either one burst of electrons, leading to this featureless spectrum, or for another carrier envelope phase, 2 points in time where electrons are emitted. And of course, they can interfere. This forms a double slit in time. And that's why you see fringes in the energy domain leading to multi-photon orders here. So you see a nice connection between this multi-photon physics and the double slit in time if we're entering the realm of Keldysh gamma smaller than 1. So that's nice. The session chair here has done a lot of work in this direction. But now we really wanted to ask the question, can we look and really understand what's going on a more quantitative basis? So how about precision attosecond physics at the surface of a solid? And there's been beautiful work by, for example, Nirit Dudovic and other people in the field who've done fantastic work at atoms. And well, again, we tried to see if we can also do precision attosecond physics at the surface of a needle tip with a field as enhanced, so we exactly know where the electrons come from. But other than that, it's not really a quantum emitter like an atom or a molecule. So to be more precise, the main question I'd like to ask is, can we disentangle yield effects? So how many electrons are emitted from the tip from these trajectory effects, from what happens after the electron is born into the field, and then it might be driven back and forth by the laser field. So that's the question, can we do that? And the idea we had is, well, maybe we can just use 2 laser fields, one fundamental at 1560 nanometer and its second harmonic, and somehow superimpose them and just scan the relative phase between the fundamental and the second harmonic. We really tried to set out now to understand what's going on. And let me show you what we can do once you have this degree of freedom. You've probably all seen this image here in one or the other form. So the lines, again, show you the trajectories. What happens if an electron, for example, is born into a single cycle of a laser field here at this point in time? Electrons are emitted when the field is negative, right? Then you basically drag electrons out. And we see here what happens, for example, for these guys, they just are emitted, then the laser field flips sign, they undergo some kind of wiggling motion, but they don't return to the tip. What's more interesting are the electrons that are emitted somewhere at this point in time. They are emitted, return to the tip, and they're the only assumption that we plug in is that when they hit the tip, that the momentum vector just flips around. So we assume elastic scattering, which is probably not at all clear that this will happen, but it's well known from atoms that it can happen. We also assumed it here. And then we just looked at, okay, what about these electrons that hit the tip and make it away? So we have 2 parameters, experimental parameters encoded here. We have the yield. I plot this here in the thickness of these lines. And we have the final kinetic energy that's color-coded. So these guys that undergo this rescattering, they can get very high energy. That's why their trajectories are color-coded in red. And the yield here is shown by the thickness. And what you see in the background, that's this black and white image. That's just the results of the integration of the time-Hamiltonian Schrödinger equation, which basically in a fully quantum picture also shows the same result that we get from this kind of mixed picture where we just model the emission dynamics with the Yulian-Ivanov model, and where the otherwise treat the electron as a classical point particle and track it with these lines here. Now, this is basically set. When you only shoot one laser field, this is what you get. Same picture for atom, same picture for molecule. It doesn't really matter. It always looks the same. What if we now mix in a second harmonic? Now it's getting interesting. So for example, let's look at this relative phase of 0, where the maximum of the second harmonic coincides with the minimum of the fundamental. There, of course, the resulting field has a smaller negative amplitude. So clearly we get fewer electrons out, right? The electron yield is just reduced just because the field is less strong. So you see here, everything is weaker. The lines are not that thick, but we get some also high energy electrons out here. What if we go to the other phase where now the maximum, the minimum of the second harmonic and the minimum of the fundamental add up? We get, of course, stronger negative field. So many more electrons. You see it here, lots of white in the background. We also see that in this TDSE simulation, very thick lines, but they are not so red. So the energy is smaller as compared to over here. And this is even more interesting for these intermediate phases here, where we get very, very red lines, so very high energy electrons. Over here, hardly any red. We can discuss later exactly, we of course understand this. This is related to the vector potential here acting. But you see now, by varying the relative phase, we have very strong effects both on the energy of these electrons, color-coded in red, and on the yield. And this is what we want to take advantage of to really understand what's going on at the surface of these tips. So what we do is now we report spectra. There's just one spectrum shown here. We see this direct path, then we see this famous rescattering plateau. We see this cutoff. From here, we can extract the famous 10 UP. So for electrons rescattering, the maximum classical energy they can gain is 10 times the point motive energy. And now we do this as relative function of relative phase between the two laser fields. So basically, we now look on top of these spectra, vary the relative phase here, and you see red means many electrons, blue means not so many. Over here, we just change the color scale. So it's continuous spectrum from here to here. We just have a different color scale so that we see clearly what's going on in this cutoff region, but it's as continuous as this spectrum over here. And what's most important here is that we can just find the maximum yield for every energy. This is this orange line, right? For every energy pixel, we just look at what's the maximum count rate, and this determines this orange line. This will be the most important line of this first part of the talk. And let me just copy the orange line down here to the results of the time-dependent Schrödinger equation. You see the orange line is almost perfectly covered by what we get from numerical results. So the blue line is the same here for our numerical results, matching perfectly our experimental results. That would be very happy. We can definitely use the TDSE results to infer something on what's going on about the experiment. But let me go one step further. This line we call the optimal phase, and I want to really try and explain you why is the optimal phase exactly like it looks here? Why is there this little minimum here? Why does it go up here? We fully understand this. It's beautiful physics, and this is what I'd like to basically try to do in the first part of this talk. And this is the only slide I'm showing you. We'll discuss everything on this slide. And let's just look into what we plot here. So we have, again, here this optimal phase. In orange, that's experimental data. The blue ones are theory results for different barrier heights. So you see, we can make the barrier shallower, or we can make the barrier higher, 8 eV, 4 eV. And let's just look at this cutoff part here, this region 3. So this region where the electrons have to reach the highest energies. Clearly, we have to emit the electrons at a time. This is what's plotted here, time. We just look into a half cycle here. When can the electrons reach this high energy? So this region 3 here is only reached here at this time, and for this region of relative phase between the first and the second harmonic, right? Only here electrons can reach this high energy. This is what we get from these classical simulations. And you see here, well, okay, this already limits the range of relative phases to here. So this part of the critical phase has to be generated somewhere in this region. And then, of course, we have to see how many electrons are actually emitted at this time and at this relative phase. And this is what we get from our TDSE simulation. So here we just see that, of course, we've seen it before, when the relative phase is pi, that means when both fields point down, so we extract most of the electrons, then clearly we have the largest yield. And if we go away with the relative phase, the yield is quickly reduced. So you see here this emission time, this emission rate, this is what's plotted here. This emission rate pulls this critical phase down just because there are more electrons emitted at a relative phase of pi, whereas the kinematics, when can the electrons reach the high energies, pull this critical phase up. So it's exactly the interplay between energy, so kinematics, and yield that determines where this critical phase ends up. And the nice thing is, this, of course, depends on the barrier height. This part here is independent of the barrier height. This part here is very sensitive to the barrier height, right? When you increase the barrier, the electrons will really only tunnel when the barrier is bent down. Only then the electrons will tunnel. When the barrier is much shallower, The electrons can also tunnel when the barrier is not fully bent down, but also a little bit earlier and a little bit later. So for smaller work functions, smaller barrier heights, this red dot here is just spread out. For larger work functions, this is much more concentrated here. And we can now uniquely determine and just basically fit. First off, what's the work function that yields the best agreement between theory and experiment, and really what do we get in terms of emission duration? And we find here that a work function of 6.6 eV, which is surprisingly large, but there's some junk on the surface, matches best. We've independently confirmed with another measurement that the 6.6 eV really makes sense. And the nice thing is now this really everything fits together here, and from this we can infer an emission duration of 710 attoseconds, even though the fundamental period length is 5 femtoseconds. So this is great, really deep subcycle emission duration. The error bar here that we can extract from our fitting routine here is just 30 attoseconds. So we've clearly now entered the realm, even though we only shoot 5 femtosecond and 2.5 femtosecond pulses at this tip, we can now measure electron emission dynamics with an error bar of 30 attoseconds. What's nice is that this is really excellent news for people interested in light wave electronics, where they really want to use the electrons to basically build transistors and stuff with free electrons based on this ultra-fast photo emission. So we were happy that these fundamental insights are also really interesting for some applications. Let me just show you something that is very recent, namely multi-electron coincident detection. Here we now have a new detector. We can detect each and every electron because we trigger these electrons with a laser pulse, and we know exactly when they arrive. We also know the energy of each and every electron. So we can now really see if, for example, two electrons are correlated either in where they hit the detector or in energy. And this is, of course, somehow related to the fantastic work that many people have been done in looking into ultra-fast correlated electron emission from atoms and molecules, you know, all this fantastic stuff about non-sequential double ionization. You can gain much insight when you look at the full kinematics of these events. This is what we see. We see that when we filter for the two electron events, that they're highly anti-correlated in energy. You see this gap here. What does it mean? When electron 1 arrives at the detector with an energy of 41 eV, which is basically just a DC voltage that we apply to our tips, it's most likely that electron 2 only arrives with an energy of 39 eV, but not 41. 41 is highly unlikely. So the electron, either one electron comes first, and the other one a little bit later. And they clearly repel each other after they are born in the field. When we integrate this, we really see there's a large anti-correlation depth. So we see 3 eV energy spacing. That's a lot. It's much more than the energy width of the electrons. So it's really useful for some, for example, heralded quantum imaging tools. And of course, we can plot the second order correlation function and see here that along this diagonal, we have a sub-Poissonian behavior. And here we see super-Poissonian behavior in these blue regions. That's of course kind of nice because all of a sudden we have now correlated electrons that we almost get for free because they're emitted in such a short time span from such a tiny source. And it's just Coulomb repulsion between these two electrons. We can also look at the time that it takes for these, or the typical time that the electrons still show this behavior. When we now shoot 2 laser pulses and just scan the time delay between these 2 laser pulses, we see that this anti-correlation gap, the 3 eV, only show up for a time span of roughly plus minus 80 femtoseconds, and then this disappears. That's a great time because it's short, so it doesn't really affect you too much if you're not interested in. But it's long compared to laser pulses that you can buy these days. So you can really take advantage of it if you wish. And let me just show you one point here. That's a little add-on because it fits so nicely to the first part. When we crank up the laser power, we also see this plateau build up here. So we, again, in this 2-electron correlation data, now see this 10 UP cutoff. So now you can really ask the question, okay, how do strong field effects and Coulomb repulsion work together? So we go back to this first part of the talk. I don't want to discuss this in too much detail, but what we see is, and this is again a point particle simulation with classical particles, they cannot cross this 10 UP line. If we now allow for correlations to be present, then we see that the second electron can basically easily shift the first electron over this 10UP line and have it reach higher energies. But this is all classical simulations. I think there is much to be gained when we really go to quantum simulations, because then you can look into quantum correlations and all this kind of stuff. So we believe there's lots of physics open here to be discovered. Excellent. Let me switch gears. Let me come to what we can do when we now want to control electrons inside of solids. In this case, inside of graphene. You all know graphene, so I don't have to tell you much about it. Let me just mention that after this pioneering work by David Rees's group, there's been fantastic work where people looked into strong field physics by observing the high harmonics emitted from the material. But there's also a lot of work by looking at the charge transfer that happens when you drive charge transfer with strong fields. And I'm going to focus on this work here that goes back now almost or more than 5 years now by my postdoc Takuro Higuchi. And I want to show you what kind of beautiful physics you can observe inside of graphene. So you all know graphene is this honeycomb arrangement of carbon atoms. If you go to reciprocal space, you get this beautiful hexagon where at the K points, valence and conduction band touch and form this famous Dirac-Cohn dispersion relation, which is very interesting. It's a zero band gap material, and you can do interesting stuff, as you can see right away. So let's just watch what can happen around this K point. And let's just look at one slide here. And what happens if we drive the electrons here in the plane, with the polarization in the plane? You know that, of course, by virtue of Bloch's acceleration theorem, we just change the K vector according to the vector potential we apply. But of course, there can also be Landau-Zener transitions from the valence to the conduction band. And I'm going to show you that there's a beautiful interplay between intraband motion and interband transition that are, of course, intricately coupled. And that's the basis of strong field physics inside of materials. We cannot decouple intraband effects from interband transitions anymore. So here now I'm going to show you the Keldysh parameter again. Now, like Keldysh already pointed out in his seminal work, what happens inside of solids. You can also have these transitions, and Keldysh parameter gets small when the frequency is small, the band gap is small, and the peak amplitude of your field is large. So that's easy to reach, especially in graphene when delta approaches zero. In other words, the Keldysh parameter basically also measures how long is the optical period of your laser field measured in the time it takes to get an electron from the valence to the conduction band. So measured in units of the Rabi frequency. Just two examples here that you can get when you simulate this, when you are in the regime of Keldysh parameter larger than 1 and you shoot a short laser pulse, then we can excite electrons from the valence to the conduction band. This is what we're plotting here, conduction band population. But you don't really see the field resolved. You see some kinks, but it's not really deeply field resolved. Now, when you go to this Keldysh parameter much smaller than 1 regime, there you see that the excitation is actually much faster than an optical period. So the electrons are excited very quickly up into the conduction band, also de-excited down to the valence band, excited up to the conduction band, de-excited again. So you see this very, very complex behavior where the excitation, as I said, is much faster than the optical field. This happens in this Keldysh much smaller than 1 regime. It's a beautiful connection between Rabi physics on the one hand side and Landau-Zener physics on the other hand side. I don't have time to discuss it. If you're more interested, please look it up in this paper. We really can cover and understand the entire parameter range, covering from gamma much larger than 1 to gamma much smaller than 1 in this term of in these terms here. What do? We just shoot these laser fields at graphene, which is here mounted in a vacuum chamber. And we have different graphene lengths. We can have relatively long graphene strips, short one, very short one. I will show you in a minute why. This is how it looks. It's a picture. It is not an artist's impression. We just shoot the laser beam at the graphene and just watch from the other side, where do we hit the graphene? And so what I'd like to convince you in the last 13 minutes or so is that we really understand now what happens inside of the graphene. There we excite real carriers. I'm going to show you what I mean by that. And what happens at the graphene gold interface, where we only excite virtual carriers. And I'm going to show you what I mean by that. In any event, this here leads to a polarization response that we can read out. This here leads to a ballistic current that we can also read out. So now we have two different ways, and I'm going to show you in the very last slides that we can build basically a classical gate, not a fantastic Fries-Monroe type quantum gate, but a classical gate where the information, the bit information, is in the field of the laser pulses. So let's just look into what can happen when we shoot such a laser field at graphene. You've seen that by Bloch's acceleration theorem, the vector potential is important. We all know that the electric field is a negative time derivative of the vector potential, so we know exactly that they two are closely coupled. And just watch what happens till here. We just take this electron here and just follow what it does. First, it just gets a little bit moved away. Then vector potential moves around. Boom, electron makes it here. And here it has a certain probability to undergo a transition to the conduction band. Then vector potential continues, electron continues, goes here, goes back. There again, the electron can go up, or this electron up here can go down. And then it just moves on. And now you can ask the question, well, what determines that the electron ends up in the conduction band or in the valence band? But you've seen there were basically two beam splitter actions here. Always when the electron is close to this minimal separation here, it can go up or go down. So this is really the analog of Mach-Zehnder interferometer. When you have an initial state here, your laser beam, you shoot a laser here. What determines if the laser beam returns to the laser or makes it to the photodetector? It's the relative path difference here and here. And over here, it's exactly the same. It's the quantum mechanical phase that the electron accumulates in the beam split state that determines if it goes if it goes up into the conduction band or ends up back down here where it started from. It's exactly the same, just in quantum mechanical language, quantum phase versus basically the classical optical phase here. This is what people call Landau-Sehner-Stückert-Majorana interferometry. And our friends from Charkiv here had a fantastic recent report overview article on this, which I can only highly recommend to you. So now the question is, which waveform drives the current? And I want to keep it short. Let's look at these two different points. So when you get a current, you only get a current if you have a left-right asymmetry in conduction band population, right? Only when electrons are here, but not over here, you can get a current. If you have symmetric population, nothing happens. They would just cancel out and you don't get a current. So we somehow have to break the left-right asymmetry. We have to break the left-right symmetry. Let's just look at these 2 points. When do we break it? Watch what happens for this waveform here. For this guy here, it passes by this point here, and there's a certain probability to undergo a Landau-Sehner transition here, and that's it. Now watch what these two guys do here. This guy's two here at number 2, they have a certain probability to undergo a Landau-Sehner transition here, and here. So very different behavior for this waveform. Whereas for this waveform, you see basically all the electrons here and here do the same, only slightly time shifted, but we are not sensitive to absolute timing. So here in this case, you would expect a similar behavior for these guys and these guys. So this would not lead to a current. Here we would expect a current. Why does it make sense for this waveform? Well, because in that case, the vector potential is maximally broken in symmetry, and it's the vector potential that governs the dynamics here. So this makes total sense. So for this waveform, this CEP, we expect symmetry breaking in reciprocal space. Of course, we can look into this in a bit more detail. We did a quantum mechanical model, tight binding Hamilton operator, where we just look at the induced current density. For the current density, it's important to know the conduction band population. That's basically all. Of course, you also need the speed of the particles, but that's easy, that you just get for free from the band structure. And then you can just integrate over the induced current density to get the charge that you generate. When you integrate over the entire Brillouin zone, that's what you expect in your experiment. And let me just show you how it looks in the Brillouin zone. So here I've zoomed in around the K point, and let's just see what happens when we now let the dynamics evolve. So we now just follow the conduction band population when the laser pulse comes in. So here you see the timing, laser pulse comes in, conduction band population builds up. You see it shaken back and forth, so big, large intraband dynamics. You see how conduction band population builds up over time. And the dashed lines here are the photon orders. So this is resonant 1 photon transition, 2 photon transition. So we see we have contributions from 1-photon transitions, 2-photon transitions. But what's most important is we have a left-right asymmetry here, mostly in non-resonant electrons. They break the symmetry, and they are responsible for this continuously increasing charge. So we just have a broken asymmetry in the conduction band population, and as long as this prevails, you just get a current. So you get a continuous charge, even though the laser pulse is gone. This is what people call real carriers. Do we see this? Well, let me at least tell you some smoking gun experiment. We now just shoot these laser pulses at graphene and vary the field strength. So for very small fields, we measure a current. This is likely due to quantum path interference. We can discuss later if you want. And then something very interesting happens. When we increase the field further, we just see that the current, which was initially positive, just turns around, becomes negative, and actually, in fact, changes sign again. So now we see very weird behavior. We don't touch the shape of the laser waveform. We only change the amplitude, and we see something very non-perturbative, right? In perturbative physics, the amplitude is just a prefactor. You would just expect that the current gets larger. That's it. No, we don't see that. We see that the current changes sign by just increasing the amplitude. So we take this as a smoking gun signature for us having entered the strong field region here. Of course, we can also simulate it. Simulation fits pretty well. It's like shown here with these solid lines. Don't have time to discuss this in more detail. It's beautiful physics, I believe. Let me show you what happens at the interface. So at the interface, right, at the graphene gold interface, the symmetry is maximally broken already. So we now have to look at it in real space. In real space, the electrons are just driven by the electric field. So now we can do the same exercise like before. Let's just see what could happen if we shoot these laser field, such a laser field here. These guys over here are just driven more deeply into the gold electrode than these guys over here. If by some magic the electrons are somehow trapped inside of the gold electrode, we also would get a left-right asymmetry. So here we would expect the largest current for this waveform, where the asymmetry is maximum in the E field. We haven't exactly figured out what it is that traps these electrons, but we have beautiful simulations from our friends at University of Rochester around Ignacio Franco, who fully confirmed this picture by pretty demanding real space simulations. This is what they get out, that after the laser pulse is gone, all of a sudden some charge remains captured, but you see it's now constant over time. So the action happens during the laser pulse, and this is why this is called virtual charge carriers that lead to the charge being transferred. The most important point is it's a different CP that leads to a larger symmetry breaking here. So we have these two contributions. In reciprocal space, we see these real charge carriers that lead to a ballistic current. It's kind of a global character. It just happens all over the place. And in contrast, we have these virtual charge carriers at the interface. This leads to a polarization that is somehow trapped inside of the gold, clearly a local character happening right at the interface. And this name of virtual charge carriers, real charge carriers, goes back many years, so we haven't phrased it. What's the signature of this? Well, we just shoot our laser pulses now at graphene, long graphene stripes, medium-sized and very short ones. And you see here, there's a lot of laser power at the gold graphene interface. So here we will probably expect a larger contribution, virtual contribution. But no, thanks. I see it here. My timer tells you I have four minutes left. Thank you. Got it. Whereas over here, there's no light on the interface. The light is purely on the graphene. So here we would only expect real charge carrier contributions, but here we would probably expect the virtual charge carriers to dominate. So let's look into this. Let's just measure current again as function of the laser peak field strength. When we now increase the peak field, we just go in this polar plot along the radial line. So you see here, this is 1 volt per nanometer, 2 volts per nanometer, 2.5 volts per nanometer. And we see the largest current for this CEP. Now we go here. We see also large currents, but now for another CEP, and here for an even other CEP, going away from pi/2, but going basically to the 0 pi axis. So clearly, we now go from the control of real charge carriers in graphene over to the virtual charge carriers dominating the physics we observe here. We thought this could be useful. Can we not build a logic gate based on this? So we thought, why not just say, we just encode bit information into the CP. Here and here. And then we let the system just sum up the two current contributions, and only when the current is larger than a certain threshold voltage, we set the output bit to 1. If the current is smaller than a certain positive current, we just say it's 0. So watch what we can do. We can now just, of course, vary the carrier envelope phase of these guys and these guys, and really just measure what we get. This is what we would expect. For example, encode into carrier phase phi A of these guys here, bit information. So we toggle between pi/2 and minus pi/2, and encode the other bit into this CP. In this case, we toggle between pi/2 and 0. See what we get. Here for this CP, if you really paid close attention, you would know we would get a positive current. For this CP at the interface, we don't get any current, but we get a positive current, so output bit 1. Check out these cases. Current flowing to the right, but now for this CP, current is flowing to the left, so they just cancel each other. No current, output bit 0. And these are the other cases, current flowing to the left, so not a positive current, output bit 0, or even larger negative current, also output bit 0. What is this? Clearly, input bit 0, output bit 1, 0, 1, 0, 1, 0 gives 0, 1, 1 gives 0. This is a NOR gate, clearly, right? And we can also build other gates. Does it work? Here's the current that we measure for these different combinations of carrier envelope phase of the one pulse versus carrier envelope phase of the other pulse. Matches almost perfectly our simulations. And we can now just pick basically certain points and define which bit is encoded into which point. And we can even come up not only with this NOR gate, we can also build an AND gate, an OR gate, an NAND gate, just by basically defining the input bit differently. Potentially, this is a logic gate operating at the frequency of the light wave. So potentially operating at petahertz frequencies. No idea if we're ever going to prove this directly, but at least this logic gate is out. Of course, we're going to be measuring soon, hopefully, how fast it is, and can we concatenate it? Can we build some kind of circuit out of it? Let me come to the end. Let me thank my wonderful group. Philip Deanspear is the one who did most of the work of the first part. Jonas Hamel here and Stefan Meyer over here are the ones who measured the correlations. And mainly Tobias Weitz, who was known until recently as Tobias Bolaki, is the one who measured the logic gate. And this was a beautiful collaboration with Ignacio Franco from Rochester. With that, let me just show you this final slide. And thank you very much for your attention. And I look forward to any question you may have. Thank you so much.
Thank you, Peter. Well, wonderful journey to the strong short pulses and how better can we understand the things based on this. So very good work. Thank you very much.
Thank you so much.
We now open the talk for questions. Okay, I see 3 hands up. Vitaly.
I have a basic question. First of all, thank you for the wonderful results presenting the basic physics. And you noted a few times Landau-Zinner model of non-adiabatic level crossing. But this Landau-Zinner model is only a very particular case of solution when the levels cross linearly. Did you see in your numerical simulations and the results really the total picture of this non-adiabatic level count?
That's a fantastic question. Thank you so much. Let me take you here. So I have one backup slide on this. Hold on, we can go right away. So we modeled this numerically. We just solved this basically 2-level Hamiltonian. And what we see is, hold on, let me just show you all of these right away. What we see is we can now just vary the parameters such that we vary the band gap here. So this would be a resonant photon energy would equal the band gap. Here, the band gap would be smaller than the photon energy, here larger. And here we vary basically the Keldysh parameter. And we see all kinds of cases. So here we see basically the very slow case, Rabi physics. Here we see this impulsive case. Here, this is this kind of hold on, where's it? Yeah, this is kind of an intermediate case. Where you see also funny looking shape, which might be somehow related to what you say. So numerically, we looked into this, but we are sure that there might be very interesting work for theoreticians to look into this more deeply to also help guide us what we can look at experimentally to figure out where are we in this. Can we look deeper into the non-adiabatic regime? So the really adiabatic regime is probably not so interesting, but it's kind of this crossing where we go from Rabi oscillation into this regime where Keldysh parameter is around 1. This regime, it could be the most interesting one. So we looked into it numerically here, but that's it, not much more. So we are very much interested in somehow learning about this more.
Okay, thank you for your answer. This is really
Thank you, Peter. Thank you, Vitaly. Now,
thank you, Vitaly.
Olga, you have a question?
Yes. So thank you, Peter. Really amazing results.
Thank you, Olga.
You can control now on really at a second scale the currents and in the standard regime. My question is about special distribution of atoms for the within the diameter of your tip. I understand that you have maybe about 10 atoms within the diameter, right? So you have a response from all of them and these discrete positions of these atoms. Do you take everything into account somehow in your calculation?
All right, thank you very much. You put your finger exactly at the point that we also find most interesting. So back with Christoph Lemel and our friends in Vienna already 20 years ago, we realized that these regular tips can probably still be considered like a flat surface because Fermi wavelength is much smaller than the tip radius. But for example, we can make sharp tips that end in a single atom. And we can also make very blunt tips. So we can basically go from the atomic physics tip that ends in the single atom to something that's really metallic. And it's very tough to simulate. Christoph Lemel is certainly one of the world experts who can say more about it. It would be absolutely fantastic to actually take our correlation experiments and try and go back and look at how are the electrons emitted. Can we learn something about this emission behavior? Exactly like you asked, what's the shape of the electron that's emitted? Can we from the correlation somehow learn something? How exactly this electron wave function inside of the metal makes it out and in the end makes it to 2 spots on the detector? I find it a very interesting question. It's very tough for our theory friends to answer because the length scales are so demanding. On the one hand side, we need to take the atoms into account. On the other hand, we have nanometers, nanometer length scale. It's a 3D geometry, so it's tough. Currently, we make very crude approximations. And I think it would be very interesting to get more insights and, of course, also more guidance from any theorist who's out there who might be interested in helping us.
Thank you so much.
Thank you, Olga. Thank you very much.
Thank you, Olga. Thank you, Peter. Now we have one last question by Laszlo. Please.
Thank you very much. Congratulations, Peter. Really great results. I'm really interested in sort of a little bit about your pulse duration of the electron pulses. Namely, you used practical and indirect measurement. So you didn't measure directly the electrons. I don't know whether you are familiar with the work of Eleftherios Choulimakis, who measured directly. And they got a quite big difference, 53 per second and not 700. What is the reason? Do you know of this big variation between the two measurements?
Thank you. Very good point. And of course, this reference should actually show up here. In another version of the talk, Eleftherios' reference shows up right here. It came out, I believe, a couple months before our paper came out. Eleftherios looks mainly at the rescattered electrons in a quite different parameter range. So when you look at everything, so we, of course, when this paper came out, we thought, oh, wow, this is interesting. Why is it so interested? Why is it so different? Why does he measure just 50 attoseconds? And I have to say, I'm blanking on it, what the main difference was, but Philip Deanspear looked into this, and he said it all makes sense. It comes together perfectly well. As you pointed out correctly, he measures this in a very different way. And I think, but I have to be a bit careful. I think it's correct that I'm saying that he just looked at basically the rescatter duration. So it's,
I mean, he used the special version of streaking.
yes, exactly. But Philip looked into this and he said it all fits together nicely. It would actually be interesting to combine the techniques.
Yeah, because then it naturally triggers the question how to make it shorter. What should you change? No?
Yes, absolutely. So we see right away that when you increase the work function, then you make the emission duration shorter. But of course, you also don't get that many electrons up here. So it's interesting. It really depends on what you'd like to have.
I see. Thank you very much.
Okay, thank you very much. And thank you, Peter, for the wonderful presentation. It really was a very important opening for the workshop, the 2 talks we had. And I appreciate the presence of all the participants. And now we have a break. Unfortunately, it's supposed to be 30 minutes break, but it will be a little less than that. And then we return with the individual seminars. So I hope that everybody that's participating in the seminars can go to the specific link, and we continue in less than half an hour the seminars. Thank you very much, and I hope you have a good coffee wherever you are. Prepare strong, weak, tea, doesn't matter. Just keep up. See you later. Bye-bye.
Thank you. Bye.